And it is, you should keep in mind they're horrible, horrible people. I do not endorse the things they do. Anyway, so enough about your mom. No, sorry. What's that?
Do you actually do that in some videos? You're just like on a tangent that has nothing to do with a particular subject. Yeah, it was just really big and uncomfortable. But yeah, enough about your mom.
Right. No, I try not to. See, because I don't like editing videos, so I try not to. But the worst thing is, like, I'm like 2/3 the way through a good lecture, and then somebody asks me a question about something, and then like I can't help myself but say something, and it's not really. It's never that bad. It's just bad enough that, given YouTube, and the direction things are going, I don't want my whole channel to be banned 20 years from now because of something I said about Abraham Lincoln 3 years ago.
I would love to see the man that has to watch an entire lecture to find the specific moment.
Oh, that's the thing, is there will never be a man who watches the lecture. It'll be a bot. Like I was watching this. There's a fellow who does videos on mostly Islam, but I showed you some of his stuff, but this was not that. This was something else, which is just clearly mocking Islam, right? Yeah. But YouTube took his videos down, or gave him a strike and banned his channels because they said that he was essentially accused him of recruiting for ISIS, which it's just unbelievably dumb that he was actually trying to recruit for violent extremists. It's exactly the opposite thing. Yeah. And then he would like appeal, and some of them got struck down, but then others did not, because it's not people, it's bots. And then maybe there's one guy who's rowing through 500 of them, doesn't really feel like looking at it, he's like, well, rejected. It's like essentially random whether or not your appeal gets rejected or accepted. Anyway, to the math. So theorem 4.9.18, let E be an extension field of F and alpha an element of E. All right, then alpha is transcendental over F if and only if the evaluation homomorphism phi alpha, all right, gives isomorphism of polynomials over F and with a subdomain of E. I'm not saying a subfield because it may not be a subfield. So in particular, alpha is transcendental if and only if phi sub alpha is injective. All right. Moreover, alpha transcendental if and only if phi alpha, which is, by the way, a mapping from polynomials over X over F, right? To E, I suppose, is 1-to-1. Now, I should remind you, what was the definition of transcendental element? It's either what? If the element is, you recall we had a definition. Alpha is algebraic over F if there exists, P of X, a polynomial, such that phi alpha of p of x, which we denote by what? We denote that by p of alpha is equal to 0. And this is if and only if it's a definition. So an element is said to be algebraic if you can find a polynomial, algebraic over a field, if you can find a polynomial over that field for which when you plug the algebraic element in, you get 0. If you can't do this, otherwise the element is said to be transcendental. Over F. And just to remind you, just a quick reminder to make sure we're on the same page. Example 1, pi is a element of the real numbers, and p of x equals to x minus pi has p of pi 0, right? So pi is algebraic over the real numbers, right? But on the other hand, there does not exist, let's say, p of x in the polynomials with rational coefficients such that p of pi equals to 0. So therefore, pi transcendental over the rationals. So when you hear people say that pi is a transcendental number, they're always talking with respect to the rational number system. Okay. So by default, if we talk about transcendental or algebraic, we take the rational numbers as a backdrop. But we try to be more precise than that in here. We try to talk about what the base field is whenever we have these kind of discussions. All right? So how are we going to prove this theorem? All right, so let's go the forward direction, right? Suppose alpha is transcendental over F, right? Then the kernel of phi alpha is what? It is f of x such that what? Well, it's the additive kernel, right? So it's the f of x which phi alpha of f of x, which we denote by f of alpha, right? Equal to 0.
So this is just mapping 0. Was that 0 was our identity?
Well, 0 is the additive identity, but the kernel of the map is the set of all polynomials which are sent to 0 under the map, which in this case is all polynomials which when you plug alpha in, you get 0. But the thing is, alpha is transcendental, right? So there cannot be anything in here except for the 0 polynomial.
Yeah.
Because if there was an f of x non-zero that was in here, that would show that alpha is algebraic. So no non-zero, f of x are an element of the kernel, phi alpha, since alpha not algebraic, therefore kernel of phi alpha is just 0, right? And we have a theorem because it is, after all, a mapping, a homomorphism, an additive group homomorphism with kernel 0. It then follows that this is a one-to-one map by that theorem we have in group theory, that if the kernel is the identity, it's a one-to-one map, right? So therefore is injective, or one-to-one if you like. And then how about the other direction of the proof here? Suppose phi alpha is one-to-one. well then, notice that phi alpha of 0, right, is equal to the 0 polynomial evaluated at alpha, which is what? Like this is 0, right? If we take the 0 polynomial, which is just multiplication by the number 0, and we evaluate that at alpha, it's still 0. So this shows that 0, the 0 polynomial is in the kernel, right? How to say this? Well, how about this? If this was equal to phi alpha, I'm not getting to the point here fast enough, f of x, right? Then since phi alpha is 1 to 1, what? I think I'm not saying this quite right here yet. I'm sorry. One more thing. So suppose this is 1 to 1, and
0 and f of x are equal to each other.
assume f of alpha equal to 0, right?
Yeah, x and alpha x and 0 are equal to each other.
Right. Notice then this. Yeah, and then because right, just what you said.
Yeah.
Because phi alpha is 1 to 1, this implies that 0 is equal to f of x, since phi alpha 1 to 1. Which then shows that no matter what polynomial we were hoping would make, alpha algebraic, we're stuck with it. It's only the 0 polynomial that takes alpha as a 0 under evaluation, right? Which shows that there does not, so therefore there does not exist, right? We just cleared up here. Therefore, there does not exist f of x not equal to 0 such that phi alpha of f of x, which of course is f of alpha, equal to 0. So therefore, alpha not algebraic. Therefore, alpha transcendental. And of course, this is all over f, right? Because this was, I'm forgetting to pepper my proof here with appropriate, this is f of x in where? Polynomials over f, right? Okay, anyway. The main reason I'm going through this proof is just to remind you the interplay between the polynomials and the evaluation homomorphism, which is kind of the major event there. Let me show you example 3 here, which is really kind of a continuation of my examples 1 and 2. But example 3, so if you accept example 2, what does this mean? This means that, let's see here. I think I skipped something. Oh, I forgot the isomorphism part, didn't I? My bad. So I've just all I did was the last sentence, didn't I? But we're also claiming an isomorphism, aren't we? So what's the isomorphism? Let's see here. So well, we've got fx, right? Mod the kernel of phi, right? Alpha is isomorphic to what? It's isomorphic to the image, right? Which is phi alpha of that, right? That's the first isomorphism theorem.
Even with the kernel just the 0 polynomial?
Well, that's the thing, is we just proved that the kernel is trivial in the case that alpha is transcendental, right? So in the case that alpha is transcendental, this is literally f of x mod the set containing 0, which is, of course, isomorphic to just f with polynomials over f itself, which then shows you that the polynomials over f are isomorphic to phi alpha of f of x, like that. And by the way, if you want a characterization of what this set actually looks like, this is just like f of alpha such that what? Such that f of x is an element of polynomials over f, right? So putting that into practice in example 3 here, we have that q of x, right, is isomorphic to q of pi. And the isomorphism is really kind of silly. I can write it down for you. Here's the isomorphism. You give me element, let's say a0 plus a1x plus da 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 plus, you know, an x to the n. So here's a polynomial with rational coefficients, right? What's the corresponding element in q adjoin pi, right? Yeah, a0 plus a1 what? So pi, yeah, pi to the 1, right? an pi to the n. So that's the isomorphism. And in fact, of course, that is nothing more. This mapping that I haven't named yet, it is, of course, the evaluation at pi homomorphism. That's the proof we just went through. Now, is that a field? Are polynomials, you know, so the question is, if it is a field, this is a ring isomorphism, right? So you can't have a field on one side and a field not on the other side, right? Yeah. We already know that polynomials over Q are not a field because the only thing that have units in polynomials are the non-zero constant polynomials, right? So for example, something like, you know, 2 plus x, the inverse of that is not an element of this, right? Because this is not a field. On the other hand, of course, if you do 1 over 2 plus x, well, that is an element of, that. I mean, that's another notation for that, but that is literally what we think of it as terms of a rational expression, q of parentheses x, right? So rational functions do form a field, where the inverses of the non-zero rational functions are just the reciprocals. So like this is the multiplicative inverse of 2 plus x. It's just that that's not a polynomial. It is a rational function. Or I really should say rational expression here, since I want to distinguish between functions and expressions.
So the base question is, can a field be isomorphic to a ring?
I mean, a field is a ring.
Yeah, but a field is complete. So how do you map points that to like?
Well, what I was saying is, because this is not a field, that's not a field.
Oh.
Because these are isomorphic. That's what I was trying to say. I just didn't get to my point. Now, the next theorem here, that's pretty much all I've got to say about transcendental elements in here, guys. Like, essentially, it's just that. If you have a transcendental element over a field, essentially, you could write polynomials in that transcendental element, and you can keep, you know, powers of pi are distinct. They're linearly independent. Powers of pi are linearly independent over the rational numbers, because if they weren't, that would imply that pi is rational, which is not. So, and of course, the giant looming claim there, I have not proved, is that pi is not rational. That's actually something hard to prove. And so, yeah. But anyway, that's about all I got to say about transcendental elements here at the moment. So theorem 4.9.20 is really the fundamental theorem of field theory again. It's really the same as the theorem I led with. It's just, it's dressed up a little bit different. So here it is. Let E be extension field of F with alpha in E, all right, such that alpha algebraic over F then there exists an irreducible P of x in F of x polynomial, right? For which equal to 0, all right? We proved all that before. Well, I guess we didn't prove that. What did we prove? We proved that there exists an extension field such that P of alpha equal to 0. This is a little bit different. So here we're saying there is an extension field, and alpha is algebraic, which means that there exists a polynomial which annihilates it. So in that case, you can find an irreducible polynomial, which in fact sends it to 0. So it is a slightly different statement than my initial theorem, but I'm just saying this feels a lot like the theorem that I led with. Okay, let's get past feelings. Here we go. Moreover, P of x is unique up to multiplicative constant. In F, right? And it's the polynomial of least degree for which P of alpha equal to 0. Furthermore, if f of alpha equals to 0 for some polynomial over f, and that polynomial is non-zero, then P of x divides f of x. So there is a lot of this that we have kind of proved in the other theorem, but I think it's good for us to just kind of go through this piece by piece. All right, so we're going to assume that E is an extension field of F with this algebraic element alpha, right? So we'll start there. Alpha algebraic over F means that there exists f of x, right, in the polynomials over F, such that what? Such that f of alpha equal to 0, right? Since polynomials over a field form unique factorization domain, what else do we know? We know that this polynomial f of x can be factored into a product of irreducibles, right? So it's like P1 of x, P2 of x, da da da, P, I don't know however many there are, R of x. That is not the way I went in this proof. Interesting. Oh yeah, this is a bad choice. This rabbit would take us quite a ways away from where we need to be. Let me erase the rabbit before it wastes more of our time. Hey, for the record, I did prepare for this lecture. No, we need to focus more on we can get everything we need by focusing more here on the fact that polynomials over a ring are a principal ideal domain. So since f of x is a PID, principal ideal domain, right? And we prove that a variety of different ways. I mean, the one way is that it's Euclidean domain, hence in terms of the degree function, and then Euclidean domain implies principal ideal domain. So since this is a PID and the kernel of the this homomorphism map is an ideal of polynomials, what does that give us? There exists, P of x in f of x such that what? Such that the kernel is generated by that, right? In fact, I believe we have previously proved that the generator of an ideal over the polynomials is the polynomial of least degree in that ideal, the non-zero polynomial of least degree. Does that sound right? I'm pretty sure we have proved this before. But setting that aside, maybe we'll recover the proof of it again here in just a second. So the kernel of this is that, and well, let me say period. If f of x is in the kernel, then what? There exists g of x, right? Such that what? Such that f of x is equal to p of x times g of x, right? So yeah, I mean, this is a result we have proved previously, is that the generator of the ideal is the non-zero polynomial of least degree that accomplishes that. So then what? And it's not just that, so that, I'm sorry, guys. I wish I could remember everything I've taught the last 3 lectures. That would help,
I wish I could remember everything you told us.
Fair enough. Okay, I actually give arguments next. Well, this much is already true. I guess it's not clear yet that the polynomial is irreducible, but goodness gracious. So how do I know that that's the polynomial of least degree is the generator for the kernel? If we take an ideal of the subset of polynomials, we can look at the okay, so it goes back to this. If you look at an ideal of the polynomial ring, right, then you can look at the set of degrees of the polynomials in that ideal, right? That's a subset of integers. So you can apply the well-ordering principle to that. And of course, it has to have a smallest element, non-zero element. And then you can argue that the polynomial that takes that non-zero, that smallest degree has to be a generator, because otherwise, if something else of smaller degree generated it, it would imply that that polynomial has smaller degree than the polynomial with least degree. So that proves that the polynomial of least degree has to be the generator. And then you can further prove that that polynomial has to be irreducible by essentially the same argument. If this was not irreducible, if it had a reduction into to non-unit factors, then then those would be polynomials of smaller degree that set alpha to 0, which would contradict.
Principal ideal, right?
Right. So what I'm trying to get at is, if I had a better memory when I wrote the proof of this, I would say, by theorem such and so forth, this is a irreducible polynomial of least degree in the kernel. Right? I mean, that's how you construct the generator. All right. So I don't want to reinvent the wheel and do all that over again. All right. So so here's another f of x in the kernel, right? And so this was if f of alpha equal to 0, and f is non-zero, then p of x divides f of x. Well, that's exactly what this says right here, right? This says p of x is a divisor of f of x. So that's the theorem. All right. I guess uniqueness, though. Uniqueness is the other thing I haven't addressed yet, right? Unique up to a multiplicative constant, right? So that's yet another theorem, right? Recall in a PID, right? Principal ideal domain, if you have this equal to, I don't know, I needed something else. Let's say p prime. Oh, I'm thinking derivative then. Let me not do that. P bar of x. Right? So if there were two different generators, what does that mean? They're the same. Remember in a PID, if you have the principal ideal, two different generators gives you the same.
Oh, yeah. That's not a UDF, like UFD.
Yeah, but it's not that they have to be equal, but what they have to be is what we call associates. So it implies p of x and p bar x are associates in the polynomial ring. What did that mean? That means p of x is like a constant times p bar of x, because the non-zero constants are the units, and remember, associates are related by multiplication by a unit. Those are the only units you have in the polynomial ring, are non-zero constants. So, so yeah, it's unique up to a multiplicative constant. All right. Now, all of this is important because it allows us to make the following definition. All right. So this is all this lead up just to be sure that the definition I'm about to write is not off base. In fact, a lot of your homework is really based on this definition. Okay. So here's the definition. Let E be extension field of F, and alpha in E algebraic over F, all right? The unique monic, what's monic mean?
Oh, is it like just one term?
No. Least degree for which? So the unique monic polynomial of least degree for which p of alpha equal to 0 is known as the irreducible polynomial. Polynomial of alpha over F. And we define alpha comma F equal to P of X, all right? And the degree of alpha over F is the degree of the irreducible polynomial. This is the degree of alpha over F. All right. So what did monic mean? The highest term is 1 or 0. Not quite. I mean, closer. So like monic, that just means the leading coefficient is 1. So like, so yeah, for example, x cubed plus 2x minus 7 is monic, whereas 2x cubed plus 1 is not monic. Let's say over whatever field you like that this makes sense in, and we'll say Q for the sake of discussion. Right? I mean, you could make these statements could be made for any field which has the numbers that I've written. You know. So yeah, monic just means leading coefficient 1. So what example was I on? 3, 4, 5. Oh, this is 4, okay. So example 5, if we look at I, an element of the complex numbers, right, over the reals, then notice that x squared plus 1, right, is the irreducible polynomial of I over the reals. Because that's the polynomial of least degree that takes the imaginary number I as its 0, right? There cannot be a polynomial of smaller degree than that, a real polynomial of smaller degree than that takes I as a 0. This we've talked about before, found contradictions. So therefore, the degree of the complex number I over the reals is equal to 2. Another example, you can look at the square root of 2, which is an element of, I mean, you can look at it as various things. I'll just say Q adjoin the square root of 2, all right? You could say it's an element of the real numbers if you like, whatever. We'll look at this over Q, right? Then notice that x squared minus 2 is the irreducible polynomial of the square root of 2 over Q. Because we can prove that x squared minus 2 is irreducible. This is kind of a heavy-handed use of Eisenstein, but apply Eisenstein with p equal to 2. 2 divides 2. 4 does not divide 2, since it's the lowest coefficient, which I failed to emphasize. We also have to have p squared does not divide the constant coefficient, right? And certainly 4 does not divide minus 2. So there you go. By Eisenstein, that's irreducible. Certainly, you cannot, I mean, anyway, it's obvious you cannot have a polynomial of smaller degree which takes that as a 0, because to do so would be to say that the square root of 2 or plus or minus the square root of 2, something like that, was rational, which is, of course, absurd. And so there you go. Likewise, so therefore, what's the degree of the square root of 2 over Q? You say it's 2? It's 2, right? Example 7, this is kind of a silly example, but if we look at pi as a real number, right? And we can look at it over the reals. And if you look at f of x equal to x minus pi, you have, f of pi minus pi is 0, right? So the irreducible polynomial of pi over the reals is, in fact, x minus pi. And the degree of pi over the reals is 1. In fact, of course, this example is rather silly. You could easily do this for what? For anything, right? So example 8, like C in a field, then, f of irreducible of C over the field is x minus C, right? Because you can plug C into that, and that's a polynomial. The issue is whatever you write down has to be a polynomial over the field, right? And that certainly is. What's stopping you from doing this always is that usually when it's interesting, C is not an element of the field. Like, I can't just write down x minus I for my example 5 because I is not a real number. So I can't do x minus I as my polynomial. But in this very silly case, I can, because any element over the field in which it's found has degree 1. Okay, stupid but true. All right. So that brings us to a definition. Oh, I have one more example. This example is less stupid. If you look at the fifth root of 2, this is 0 of, well, x to the fifth minus 2, right? Which, by the way, is irreducible by Eisenstein with p equals to 2. So, in other words, the irreducible polynomial of the fifth root of 2 over the rationals is x to the fifth minus 2. And, of course, we can see here the degree of the fifth root of 2 over the rationals is 5. And there's nothing stopping you from doing the sixth root or the seventh root or you pick it, right? Because you can also prove it's irreducible by Eisenstein with p equal to 2. So, anyway. So, definition.
What happens with particular fractions, like degrees?
Particular fractions.
X to the 1/2 minus 1 plus 1.
X to the 1/2.
Plus 1. Or, well, that one's over Q. Okay, never mind. Well, no.
Like what is, you mean like 1 plus the square root of 2?
No, like, you know, like.
I mean like 2 to the 3 halves power or something? Well, I don't know. I'll do it up here. If I look at alpha equals to 2 to the 3 halves power over q, and I set out to find a polynomial which takes that as a 0.
Okay.
It may or may not be possible, right? It's not possible for e, it's not possible for pi. Is it possible it's not possible for some algebraically constructed number? I feel like it's unlikely. But so square both sides, right? So it looks like x squared minus 8 is probably the irreducible of 2 to the 3 halves over q. In fact, that's not, and maybe I could even, I'm not sure that's actually true. I think that's true.
I get what you're saying. You think there's sometimes like you can.
Well, I'm just,
go a different route.
well, what I'm worrying about here, and this has to do with the definition I'm about to write. So let me write the definition. Remind me to circle back to that. Let me write this definition. A field E is simple extension of F if E is equal to F adjoined with alpha for some alpha in E, alpha not in F. Did I say that? I don't say that. I guess I don't say alpha not in F, but alpha not in F is where I want, really what I want to. That's usually what I want, but that's not here. Fine. So we define, and I said this before, but we define F sub alpha is the smallest field containing what? Both all the elements of F and alpha. Okay, so, and likewise, F alpha comma beta, smallest field that contains F as well as the elements alpha and beta. And similarly, if we write F of alpha 1, alpha 2, dot alpha n, same thing. It contains, it's the smallest field containing F and all the elements alpha 1 through alpha n. All right. But simple extension that implies just one thing. Like this would not be, if this cannot be written, this is not a simple extension. The only way F of alpha comma beta could be a simple extension over F is if there existed a gamma such that this was just equal to F of gamma. If there was something else, gamma, that this was an extension by gamma, then great. To give you an example of this phenomena, if you look at Q adjoin square root of 2 and the square root of 3, well, I believe that, and I could be wrong about this, but I believe that's Q adjoin square root of 6. Can I get square root of 2 and square root of 3 from square root of 6? I could be wrong about this. I'm just, it's probably more complicated. So like square root of 6 times square root of 6 is what? Yeah. So let's see here, square root of 6. Well, square root of 6 over 2 squared is what? Well, that's 6 over 4. That's not helpful. Curses. sorry, I can't remember how to get. Oh, so square root of 6 is square root of 3, square root of 2. I'll tell you what, I'm for now, rather than burning class time on this, I'm going to leave this as a question. You guys can prove or disprove this, all right? I'm not sure. I will think about it. I can't see the arithmetic at the moment in my head. Now, this theorem we've used before. You know, let E be simple extension. E equal to f of alpha, right? For some alpha algebraic over f, right? With the degree of alpha over f equal to n, which is greater than or equal to 1. Well, fine. Then for each beta in E, all right, there exist unique B0, B1, Bn minus 1 in F, for which beta is B0 plus B1 alpha plus B2 alpha squared plus Bn minus 1 alpha to the n minus 1. What this theorem is actually saying, right? Let me just put it out there. What this theorem is saying, in other words, that is 1 alpha, alpha squared, alpha to the n minus 1 forms a basis for f over alpha as vector space over f. Now, you might not recognize that as exactly that, but that is what it's saying, because it's saying that it's a spanning set. See, because any beta in E can be written as a linear combination of 1 alpha, alpha squared, all the way alpha n minus 1, right? So what do we need for it to be a basis over a vector space over a field? We need it's a spanning set. That's what this says. We also need linear independence, but linear independence has a number of different characterizations, one of which is that the coordinates with respect to the basis are uniquely chosen. There exists unique coefficients. That is tantamount to claiming linear independence of that set. Okay, so how does the proof of this go? So proof looks something like this. If the irreducible polynomial of alpha over f is equal to p of x, and we'll give some things here, which is monic, right? So it's x to the n plus an minus 1 x to the n minus 1 plus plus a1x plus a0, right? Then, of course, we know p of alpha is what? 0, right? By construction, p of alpha is 0, since it's the irreducible polynomial of alpha. So by construction, it's one of the polynomials which sends it to 0. In fact, it's this polynomial of least degree with leading coefficient 1 for which that happens. But what's that tell us? Well, that tells us that plug in alpha here, right? So thus alpha to the n is equal to minus an minus 1 alpha to the n minus 1 minus dot 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 minus a1 alpha minus a sub 0, right? And I'll write this more succinctly as the sum k equals 0 to n minus 1 of alpha sub k, excuse me, a sub k alpha to the k, right? And I'm going to call that star for reference, right? So I say the smallest field containing alpha and f is given by the quotient, you know, f of x. So we think of E as being what? F of x mod the ideal generated by P of x, right? Where alpha equals to what? X plus P of x, the ideal generated by P of x. So is smallest field. Containing alpha and f, right? By our previous discussions and calculations, this we already know. All right, but what is an arbitrary element? What does an arbitrary element of this E look like? So if beta is an element of E, right, then what? Beta is equal to, how does it look like? Well, beta is equal to, we could say B0 plus B1 alpha plus B2 alpha squared plus dot 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 plus BM alpha to the m, right? So this is just using the identity that we talked about before, that the notation alpha, right, is a shorthand. X plus P of x, right, is alpha by definition, and then like x to the, you know, j plus P of x, we talked about how that's equal to alpha to the j. So because an arbitrary element of E is like a polynomial plus the ideal, you know, the representative is the polynomial of, say, order m plus the ideal, and then we apply this identity order by order using the properties of coset addition to rewrite it as this. But I'm claiming more. I'm claiming that can be further reduced. So, how do I say this? So if m is less than if m is less than n, then we're done, right? I need to come up with a name for this thing up here, which I'll call it Pac-Man. Then Pac-Man true. Because it's, you know, it's a linear combination of those things. So let's suppose well, what I want to do is I want to prove this by induction. I'd like to prove this by induction. Induction on m greater than or equal to n. And so here I'm assuming that